Is the other class empty or is it still there?
What's that?
Is it still empty next door or they're
I
there?
don't know, we'll find out. Looks like we're all in here. All right. In the summer, people running out of gas a little bit, I think. People travel. Okay, so we started talking about two asset options last week, and we also started talking about Monte Carlo. And we're going to continue those themes this evening. Okay, so there's a chapter 21, which we kind of cover in detail, but I think it's worth mentioning so you just know what else is out there that we haven't talked about. And basic numerical procedures. So we've been working with the Black-Scholes formula, the hallmark of which is it's essentially a closed form solution, where closed form means I'll tell you, in the case of the Black-Scholes model, like 5 numbers maybe, S, K, F, R, sigma, and T. I guess that's 6 numbers. And it will do some arithmetic on it and come back with an answer. And you can get your Greeks like that too. I'll point out that baked into baked into Black-Scholes, right? There's this, this hidden formula ND1, right? Which we remember is equal to the integral from minus infinity to D1 of the, I'm just going to call it P of X dx for a moment, emphasize this probability density function. You might as well just remember it's just the density function of the standard normal distribution. So the sigma has been buried into a standardized calculation, which is basically a z-score, right? What is I guess one reason why the letter z is often used here is the so-called z-score is x minus mu over sigma, right? Which is how many standard deviations is x away from the mean, right? Our mean is 0, of course, when we get to the standard normal, but in the Black-Scholes world, the mu is actually r minus q, and it's recognizing that what's important is how far, every normal distribution in some sense is like every other normal distribution. The only thing that changes from one to the other is the units change, right? If you measure someone's height in inches versus measuring their height in centimeters or in meters, or you weigh them in kilograms or pounds, or you do an IQ where the scale is from centered on 100 or centered on 1,000, doesn't really matter. In the end, all bell curves are essentially the same. They're just defined by their scaling. And that's why the standard normal distribution is used. And then to get this probability, which is why I use the letter P of X, right? You have to understand that n is a cumulative. Oops. Let's see if I can do that. N is a cumulative distribution function, which means we're going to find the area under this curve. And then the question arises, how do you get that area into the curve? In calculus, there are some problems you can do by hand. For example, we have this parabola. Actually, let me make it better. Even better than parabola. Let's take the line y equals, I'll just be a little generous here with the fraction, 2x, right? And let's do it from 0 to 1. So what's the area contained inside this area here? Well, that's a triangle, right? So you can see this is 1 unit long, and y is 2x is 2 units high, right? So the area is equal to half of the base times the height, which is just 1. So that's 1. All right. Or you could think about this. This is like twice as big as a unit square. Do the 2. The unit square would be 1, right? Twice as big would be 2. Well, it wouldn't be a square anymore, I guess. And then this is done by calculus, right? You take the integral of the function, 2x dx, right? and you go from 0 on the x-axis until 1 on the x-axis. Right? Calculus does this same problem, putting the function here, and this integral sign needs area under the curve in this context. And it starts where x is 0 up until x is 1. And if you remember calculus, right, or if you've seen this in calculus, the antiderivative of 2x is x squared, because the way the calculus does it is 2 comes in front, the exponent drops down, and you get 2x. So evaluate x squared at 0 and 1, and you put the 1 in, and you subtract the 0 getting put in, and you just get 1. You get the same answer. So not surprising, you get the area under a line is equal to the area of that rectangle. I mean the triangle, right? But calculus gets the same answer, which is good. It's always good if you develop a method. Let me try this method on some other thing I know the answer to and see if it works. This is a general rule, not just for mathematics, but for your daily work in the job market, when you're working on the job, right? You come up with something, and I say, I think this is the method that's going to give me the right answer, and does it work? And so I think it works. I did everything carefully. Maybe I've done it twice. Maybe I did it, and my friend did it too, and we both agree that we did it right. It's always good to have many people thinking about it, and you'll always have people asking you questions. How do you know this is right? Well, what about that? Did you think about this? Did you think about that? Because when there's money on the line, especially, or lives in the case of other industries, right? You have to be sure. And one of the things you can do before you start sharing with other people is you can, that's my thing going crazy there. Hold on a second. You have so many apps these days, right? Like, I mean, my job, right? We have Slack for communicating our general daily work, right? We have Signal when we want to communicate stuff that's like extra private, less vulnerable to interception, hacking, whatever. We do a lot of that on Signal. Then we have Telegram for talking to our clients, and they're always all just, you got email. Once in a while I get an email like, who is sending an email from my company? Because I'm here at my desk. It's hard to keep track. And sometimes we have conversations live in all 3 of the messaging apps simultaneously. And you're like, and there's like 5 conversations going on. How do you keep up, right? And I definitely don't have those noises on my daily machine, because that would just drive me crazy. Okay, so, but one way you do it, you say, look, I developed a calculus technique for integrals. I apply it to a problem which I know the answer to from regular high school geometry, and the answers agree. That's good. It's not proof positive, but it's a good start, right? And but now when you get this normal distribution, this guy does not have a closed form solution. There's no algebra or calculus that you can do that will give you exactly the value of NV1. But there are techniques that enable mathematicians and computer scientists, or scientists in general, to approximate the integral. And it used to be like, say, prior to 2000, these things would be in books. You may still pick up an old, even a stats book today, a lot of them will have the table of normal distribution values, where you'd look up the D1, essentially the Z value, and you'd look up 2.33, and the cumulative area would be, I think that's like that's 97.5%, or maybe it's 99%, right? Okay, or you do what's n of, for example, just kind of a little off your head, what is n of 1? Let's pretend this happens to be 1. Anybody know what n of 1 is? I should say everybody here knows what n of 1 is. The only question is, can you pull it out of your mass of gray matter?
You mean a z-score?
What is it?
You mean a z-score of 1?
Yeah. No, what's the normal distribution cumulative from minus infinity? Remember, n, by the way, it's sometimes in math circles, it's often also denoted by capital phi, okay? But in Black-Scholes, it's always called n. It's called n in a lot of places.
Well, it's going to be 0.5 for the negative numbers. Then you're going to add the one standard deviation, it's 67, so 67 minus 50, it's gonna be around 67.
Close enough. So the rule is one standard deviation is what, 68 point, whatever. Right, but I think it's really like 3413 is the amount to the one standard deviation. Right, so you know this answer if you don't think. It's 50% to get to the halfway point because of the symmetry, right? And it's another 34.13. So this number happens to be, 0.8413. And what does cumulative probability means? Cumulative probability means that the set of outcomes that are being measured by whatever this probability is, 84% of them are 1 or less. And consequently, 16% are 1 or more, okay? But there's no simple formula. This formula from calculus, where the integral of 2x happens to be x squared. There's a lot of problems you can solve by yourself. Stephen Wolfram, the founder of Mathematica, the owner essentially of Mathematica, his first really interesting hobby, as it were, when he was a student at MIT, I guess back in the 80s. He's a British guy who has a very high opinion of himself, I think. I've seen some quotes, but he is actually a genius, so I guess that's what happens. I get a little smarter, maybe I'll think more highly of myself. But he developed a computer program that would take any function that you gave it, and if there was a set of manipulations that you could do to get the exact answer, remember, take away the 0, take away the 1, you're talking about integrating a function, the result is another function, right? That's what calculus is. Integral of a function is a function. The derivative of a function is another function, right? He came up with a program that would be able to take pretty much any problem for which there was a finite set of steps that you could do to get the answer. His program would get the right answer. It's like the best integral calculator that there is right now. I'll show you one at another point. But you go to wolfram.com or Google Wolfram Alpha, whatever you need to do calculus. So in Calculus 2, there's a whole month or month and a half of learning all the kind of tricks that people have figured out. But in the end, really figuring out using numerics is just as good. It may not be as intellectually satisfying to have the exact answer. So you go back to the Black-Scholes formula, right? The call price is equal to e to the minus RT FNU. This is what we call a closed form solution. It's very satisfying that you could write down a simple formula and get the price of an option, right? This is a good thing. Not only that, because of the calculus, you can take the derivative with respect to spot and get the delta, right? But buried inside that quote unquote closed form solution is this function n, the cumulative distribution function of the normal distribution, and that actually is not known analytically. When something has a closed form solution, we often say we know it analytically, which just means that I have a formula based on that I can apply to get the answer. So it looks like this is an analytic formula, but it does rely on the fact that n is computed using numerical methods. And if the normal calculator was weak, in the sense that it made errors in maybe in extreme cases, you potentially have an issue. But normal distribution obviously is intensely studied, so pretty much any value of D1 you get in there is probably going to have something like at least 10 decimal places of accuracy, if not 16. The most you get on most computers is 16 decimal places of accuracy. That's just a function of the numerical, of the digital computation paradigm. You only have so many bits or bytes of information, and you can only be so accurate with 16, what a floating point number is double is, I think it's 32 bytes, or 64 bytes, I guess. So that's baked in there. But there are other problems for which it's not even possible to express it into this simple formula where the only thing left undone is the calculation of the normal distribution. And for those, mathematicians in finance developed numerical techniques, and I'm going to show you those. Before I do that, I want to say one more thing about this. We're sticking to the case really of the European call option. We can also talk about exotics and even vanilla option. I mean American style options. So you have this. Let me get rid of that one. You have this, t = 0 axis, right? And then you have, let's call it little t = 0. And you have this little t = capital T. And the model says that when we get out to capital T, there's going to be a distribution of prices, which is log normal. Now this is a little bit upside down because it actually makes sense. This is, s at time t = 0. This is the s at time t = infinity if you go that way, right? Even though if this was a y-axis, up would be positive and down would be negative. Log normal never becomes negative, right? It becomes, it's bounded below 0, right? If I were to draw well, you can see the picture, right? But this is essentially this is the probability mass axis. And with the normal distribution, what the geometric Brownian motion does, it's, hey, shoot a path and it lands over here, or shoot a path, maybe it lands over here. And the cumulative normal distribution will tell you the probability that you end up in the money. It turns out the probability that s at time t is greater than the strike, for example, if it's a call option, is equal to n of d2. So that's actually the function of d2. It's a probability. Don't forget what happens when you get there is if you pass the strike, then you have to pay the strike to exercise your option. So this is actually when you take that component of the formula, you have the discounted value of the money you're going to have to pay to exercise times the probability you're going to have to exercise. This one's a little more tricky. This is you take the forward price of the asset seen from today, and you weight it by the probability. How much is this in the event when you exercise? How much is it worth? And you see the difference, which is that no matter how deep the money the option is, K is just a number. It's $100, whatever the strike is, and the liability side of this, the minus sign, liability is minus, right? Is just that $100 times the probability that you get past K. But the asset side, which is you're going to receive the asset, is equal to the forward weighted by all the possible outcomes. When you just, if your strike is 100 and you get to 101, you're only making $1. It's not that valuable. But if the strike is 100 and you get to 150, you're making $50 when you exercise. That's very valuable. But of course, you're less likely to get to 50 than you're 150 if you already get to 101, right? Probability is, especially in terms of moneyness. So we have this model that says, okay, I need to understand this distribution of final numbers that are produced by the geometric Brownian motion process. Remember, the geometric Brownian motion process, right? This is, s of time t is equal to the initial price times, I'm going to put a mu here, e to the mu t plus, a sigma t root t z. Okay? So the z is the normal distribution that's kind of hiding in there. And that you let z take on all the values from minus infinity to infinity that the normal distribution takes on, and s at time t fills out that log normal distribution. And you can see why it's always positive. It's because you're taking the exponential of something, and exponentials are always positive, right? E to the minus infinity is 0. You never go negative with the exponential, right? And that captures the limited liability nature of stocks, right? If Apple goes bankrupt, that's it. It gets to 0, but it's done. If you buy Apple stock, you don't have to pay people back money if Apple owed people money. Your liability is limited. We talked about that. That was really one of the innovations of 1400s in Italy that made corporate capitalism really take off. The ability to take a chance without having to go into debtor's prison if you're bad at business, right? So although we have a Black-Scholes formula for getting this distribution. There are other ways to get that distribution. The first way that we're going to kind of gloss over pretty quickly is the so-called the binomial tree method. I don't know if you've ever seen this, but I want you to at least be aware that it exists. That's not that one. This is my mail. Okay, what happened? Oh, because I turned off my internet. A second here. Put this on here. Second. So the message back end must be busy out there in Workland. Okay, where's my Gmail? Okay, so in the binomial tree method, first of all, binomial you probably know means two terms, like in polynomials, there are two terms are called binomials. So, approaches to derivatives valuation. So far we've undertaken one, which is the closed form solution. That's Black-Scholes. For the price of a forward, we have a formula, we priced that. All of the other options we've talked about, double no touch, reverse knockout, etc., they also have closed form solutions. Last week we saw the Margrave option, which is just the option to exchange one asset for another closed form solution. Three other methods that are not closed form, that's why they're called numerical methods, are trees, Monte Carlo simulation, and finite difference methods. We're going to spend some time on Monte Carlo, like we did last week, but let's just touch base on what a tree is. So what a tree is, and this is covered in the book, is that it says that, look, at each moment in time, this is a simple model, we'll see why it nonetheless has a lot of utility. At each moment in time, the asset price, whatever it is right now, S, will go up to some multiplicative factor, S times U, so U might be 1%. So maybe it'll go up by 1%, or D, 0.99 times S, maybe it'll go down by 1%. And there's probabilities associated with that. P for going up and 1 minus P for going down. Why is it P and not some other number besides 1 minus P? Because it's a probability, right? And there's only two choices, up or down. You always have to add up to 1, right? Either it went up or it went down. We'll see a trinomial tree in a few minutes where we allow the middle possibility, it does nothing. And they talk about, if you have this is just kind of remembering some of the themes. Black-Scholes started with just the R, the risk-free rate of interest being important, but then quickly other people modified the model, Black himself, to include a dividend of Q. And it turns out, so, what is this parameter of a tree? Keep in mind, we're saying given S today, we want to know what S will look like in the next period. These are called period models. And what you'll do, if you had a 1-year option, you might have, you might take one step every day. You have 252 steps, let's say. or you might do something else, but those would be called periods. Each period, you're defining a probability distribution. S started here, and then it ended up either here or here, okay? So the parameters for the model, which are not that important to us, is just that the mean, which is given from the forward price, e to the r minus q times delta t, the size of the time step, is going to be given by pu plus 1 minus pd, and the variance is given by this other formula, and then one more condition. It turns out, so how many variables do we have? How many variables are there in this probability distribution? How many numbers do you have to tell me in order for this probability distribution to be completely specified?
Right there at the top, just the two, the S and the P.
You got to tell me the P, right? S is just part of the, S is an input to the model, right? It's the current spot price. But you got to tell me the probability. So P could be 60%. The bottom would be known. 1 minus P would be 40%, right? Whatever you pick for P, 1 minus P is going to be the other one, okay? But you also got to tell me a U, and you got to tell me a D. There's no reason why U and D have to be related in any way at all. U might be a 10% up move, and D might be 1%. It could be a 1% up move. They could both be up moves, even though D is meant to suggest down. I don't think there's a strictly speaking mathematical reason why D can't be down. Certainly, if the process is drifting up a lot, very fast, either it goes up a little or it goes up a lot along the way. So you have three parameters, right? And then what they do is they say, if we define, well, look at that sentence for the mean, right? Well, what is that saying, right? That's saying that, well, let's just take a look. Let's draw it out for ourselves a second. And we're saying that S will go up, or it will go down, right? Okay, so what's the mean value of S at the end of the period? Mean after one time step how do you get the mean? These are the two outcomes, right? So how do you get the mean? Is equal to, mu, let's not use mu because we're using, we can use, let's call it, let's call it S bar, which is another term for average, right? S bar is you went up with the probability of P, right? And you went down with the probability of 1 minus P. So this is the two places you could have ended up at, right? That's how you get an average, right? And because P and 1 minus P are really weights that add up to 1, you don't have to divide by the number of inputs, right? If it was an arithmetic average, when I do a weighted average of your grade, right? It's 30% of this, 40% of that, 30% of that. So if they give you 3 grades like 100, 100, 100, you just add them up. That's what you're going to get, right? But the only thing important there is that the 100, 100, 100 all be on the same scale, otherwise I'll be screwing up, right? Okay? So that's the average, right? And what do we want the average to be? This is a different question, right? But one good choice is we'd like the average to be this. And why do I say it's a good choice? Because we want the spot to drift towards the forward on average. That's what happens in the geometric Brownian motion, right? The expected value of the spot at time capital T is just the forward. All of the good outcomes, all of the bad outcomes, weighted by their respective probabilities, land you right on the forward. That's the way the model is set up, okay? So that's where the requirement is, factoring out the S, we just end up with, we want PU plus 1 minus P times S to be equal to e to the minus, what's the forward? The forward is this thing, times S, where I move the S to the other side. So that's the requirement, this would be a D here, right? That's the requirement that the weights probabilities multiplied by the up and the down shock, we want them to equal e to the minus R cubed minus T. And that's given in this formula right here, okay, the first one. Then the second one, what's the variance at the end of one time period? We talk about Brownian motion, geometric Brownian motion, specifically, both actually. Variance is additive, right? So if you take, tiny time steps, each one contributes sigma squared to the variance. Well, in our case, sigma squared is only going over one period of time. That's the total variance. Remember, we emphasized a lot. When you want to think about the Black-Scholes world, remember, this class is not only just about learning how to price a vanilla option, you can get it off a screen, right? It's about understanding that sigma squared and T show up in all of the Black-Scholes formulas together, which is another way of saying that the amount of uncertainty you experience is the product of variance and time elapsed. And if you want to put your uncertainty back into standard units, you would say sigma times the square root of T. Why do you do, that's kind of weird, right? So sigma is in, like if Apple's $100 and I say sigma is $10, sigma is a number that's in the same scale as Apple. If I say sigma squared for variance, I might say the variance is, 10 squared. And you get squared units, which are a little weird in terms of money. But then we put the burden back onto T. Instead of saying it's per year, we're saying it's like per square root of a year as a okay? So how many variables do I have free? What I just said. How many variables are there to define this model? There's P, there's U, and there's D. So there's 3 variables. How many conditions have I imposed? I've said I want the mean to force this condition. I want the variance to make me have the total variance in the period, right? But I have a third free parameter to pick. And we have to define some way of picking that parameter. A common way of doing it is that the up shock equals 1 over the down shock. So if what's that saying? Let's just see how that plays out in math, right? Which is up equals 1 over D. So if up is equal to 100%, 1%, right? 1% move, then down would be equal to 1 over 1.01. So it wouldn't be exactly 99%. It would be only approximately 99. Okay? There are other choices that you can do for U and D. They're related. Or there are other ways to bind down the last free parameter. And different ways yield slightly different models. All of which in the limit, which means that the number of time steps goes to infinity, the size of each time step, the delta t, goes to 0. In the limit, they all end up producing the geometric Brownian motion, which is kind of the whole point that makes the model useful. And what he did over here was, he said, look, if these are the requirements, then this is the solution. U will be e to the power sigma root t, delta t. D is the inverse, so you get a minus sign there, that's nice. And then P will be the forward drifting parameter minus D over U minus D. And if you do that, you'll find out that the mean after one period is the forward, the variance is the amount of variance, sigma root T, variance of returns, by the way, not variance of outcome, right? Okay. And then what happens with the tree is it does this, right? So take a look at this for a second, see if you can understand what's going on here. What this says is that in the first time step, S either goes up and ends up at S times U, or it goes down and ends up at S times D. Then there's another time step that takes place. So let's say I want to price a 1-year option. I start from today and I move out 1 day at a time. Each day I take a value. Well, when you get to the up state, you still have a binomial tree. There's 2 possibilities. It goes up, so you had a U and a U, so now you got U squared, or it goes down, we'll see, we'll come back in a second. On the bottom tree, it goes down. So what happens if it goes up and then it goes down? So if it goes up, so let's draw that back on the notability here, right? So just the two steps here. Okay, then once you get to this node here, this is S0, and this is S0 times U. Now you take another step. This one is going to be S0 times U times U. This one's going to be S0 times U. We don't really need S0, you know, we can get all those zeros. It's obviously S0. Okay, so this one was SU followed by a down step. So it's S times U times D. Now on the other side over here, S went down, so it got multiplied by D. Then it goes back up, which is just going to be D times U, but that's the same as U times D. And over here you have S times D squared. And then here's where you apply the fact that U is equal to 1 over D. So this is just equal to S. So the way this particular version of binomial tree is set up, an up step followed by a down step is unchanged after 2 periods. And that's only 2 periods into the tree. And what happens in the bigger diagram, right? You can see 3 periods. So after 2 periods, after 1 time period, you can be in 2 places. After 2 time periods, you can be in 3 places. After 3 time periods, and then 4 time periods. By the time we get to 4 time periods, we have 1, 2, 3, 4. Okay? Now you just have to use a little bit of imagination. We could Google image search, it would come up as well, and understand that if we did like 100 time steps, first of all, if we did 100 time steps, how many nodes would there be at the end of the tree? Nodes being how many prices are we allowing S to experience?
It's going up by 1 each step by the looks of it.
Yeah, going up by 1 each step, right? Therefore,
101.
101, right? Times 0, we had 1 time step. I mean, 1 price. Today, there's only 1 price, it's the price, right? Next time period, we've got 2 time steps and so on. So then you have 101 prices. Is that a good enough representation of the final value? Let's just say it was Apple, and let's just say the drift was 0. So the middle would still be at 100. You'd have 50 prices above 100, 50 prices below 100. How spread out would they be? Well, if you figured out what the top node would be, which is just S0 times U to the 50th power, right? And then if you figured out the middle node is 100 again, there would be basically some version of equally spaced. But you can see what happens at the end of the tree, right? I probably do a joint window. Let's see. There's a way to do that. I knew what I was doing. Anyway, at the end of the tree, right? Oh, by the way, what's the probability that you get here? The upper node. What's the probability at 2 up steps in a row? Probability going up.
It's
Right?
1 out of 4.
No, not in this case, but not a bad answer. P is the probability you went up the first time.
Oh, okay, I see what you're doing.
Yeah, P is the probability you went the second time. So this probability is P squared, right? This probability is P times, this is 1 minus P. This is P times 1 minus P, probability. And this one is, 1 minus P times 1 minus P, right? Those are the probabilities, because probabilities multiply. If there's he said 1 over 4, which isn't a bad answer. It's actually one of the choices sometimes made is to set P and Q equal to 1/2 each. That's a choice that is made sometimes. And then manipulate U and D to get the correct mean and the correct variance, okay? And so in other words, you set P by fiat, and then the other parameters are used to satisfy mean and variance. Yeah, so if it was a half times a half, it would be a fourth. But in this case, P is going to be some number probably like 0.53, and U is going to be, and 1 minus p is then like 0.47, so you end up with some number that's not exactly symmetric. The asymmetry is caused by the fact that the drift is non-zero, basically. Okay, and then, so that's that. So then what happens at the end, you know, you get to the final node, right, you have here, you know, it went up, let's say we said 100 times, right? Every time it went up, right, that's gonna be a great year for you if you're Apple, right? Like we went up every day, we just kept going up and up and up by the same amount, 1% a day. End of the year, Apple owns everything. And if you own Apple stock, you own a piece of it, right? The probability of that, right? Probability of S times, let's call this price S101, because it's going to be the 101st price, is going to be equal to P to the 100th power. So what is P to the 100th power going to be? P is a probability. It's probably around 50%, but you know, even if it were like 60% or something. What happens if you take a number smaller than 1 and multiply it by itself 100 times? A half times a half times a half, 100 times. What number is that?
Essentially 0.
Practically speaking, it's 0, right? It's 1 over 2 to the 100th power. And in fact, on a computer, it would be 0 because it's not enough decimal places. You'd have basically some number of decimal places like 75 or something. 75 zeros followed by a 1, right? So you don't really get there, right? That's the real tail. This were now I've got it upside down. But you know, you don't get to the tail. You don't. You know, the stock price never goes to 0. It never goes to 1 million either. Although there's a very tiny probability that it could, right? And what happens at the end, right? You've got all these prices, right? You've got, let's call it S. Let's call it S. I'm just going to call it S. Yeah, S. Let's call it SN, right? So SN. Let me change that. You know, at the final step, the nth possible value of S is going to be equal to the initial price times the up step happening n times, and the down step happening capital N minus n, for little n is equal to 0 to capital N. So capital N, I said maybe there was 100 time steps. So it's possible that it never went up. U is to the n power is u to the 0. It always went down. Or it's possible it went up every time, in which case u gets the capital N power and d gets the 0 power. Or any possible number in between there, right? That many ups and that many downs. Right? That's the final payoff. And you know, if you're paying for a call option, right, the value of the call is equal to, and then what you do is you take, so you build the tree with all those prices, and you take S sub n, and you multiply it by u to the n times d to the n minus n, and you take that number and you subtract the strike, and you take the positive part, because you only exercise when you're doing the positive part, and you let little n go from 0 to capital N, right? So you know, you create this binomial tree with 101 steps at the end, and you take every price that it could possibly be, you subtract the strike price, you take the positive part, okay? That is missing one thing, which is, I want to call this, I'm going to call this P sub little n, where P sub little n is equal to, you got P n times, and you got 1 minus P. You managed to have this many up steps and this many down steps. So now I've taken all of the monies you're going to make by exercising this option on the tree, multiplied them by the probability of them happening, and I need one more thing to actually get the Black-Scholes price. What is it? Or to get of this approximation to the Black-Scholes price.
You said what is delta T?
What goes in the front of our Black-Scholes model? It's not been incorporated here yet. What's in the front?
What time?
This is the discount factor, right? So you need to have the discount factor. And consequently, once you put that discount factor there, you have actually have a value for the call. Now, an interesting question that you'd want to, so let's say you're a risk manager, you're the head of risk at Goldman Sachs, circa, let's say, 1987, and some young whippersnapper out of math school comes up to you and says, I could price a Black-Scholes option using this formula. And you might say to them, well, what's the point of that? We already have the Black-Scholes formula. And you say, well, there is a point. I'll come to what the point is in a second. But this formula will give me the Black-Scholes price. You say, okay, well, what do you say is the risk manager? So one of the areas that risk managers work in is what's called model risk management. Model risk management is about, every bank especially, but also other firms besides banks, have model risk managers who are responsible for reviewing all the details of every mathematical model or financial model that the firm uses to try to make money. And they look at the model and they say, A, does it make sense? Is the math good? Is the finance good? B, did they implement in code accurate or spreadsheet accurately the model they're claiming? And C, is the model preserved in a archive so that we can always access a mint copy that we know is not going to be broken? Is the source code controlled? And if we can assert to all these factors, and then we might say, what are the shortcomings of the model? I worked in model risk. What was my group called? Model validation, it's called. I worked on model validation for a while. You ask, you look at other people's models and you say, am I satisfied that this is a reasonable representation of the type of risks to which the firm is exposed? And what's the process for becoming satisfied? So you might say, okay, well, I agree with you. If you have another way to price a vanilla option, that's kind of interesting. In fact, it's interesting for the following reason. Maybe it gives a different price than the Black-Scholes, at which point you might ask the question, that's interesting. It's different. Which one is the right price? Now, Black-Scholes, of course, is the standard price, but that doesn't mean it's, it didn't come from heaven. Here's the price of an option, right? There's a good mathematical theory to why the Black-Scholes is a useful model, but there's no reason to think that some other model would not be also useful. And you might decide that this model is even better, and by me pricing options this way, I can actually outfox the market, which is using stupid Black-Scholes, and make money for the firm. Or I could find out that somebody out there in the shark-infested waters of financial trading is arbing me at Goldman Sachs by, we're only charging the Black-Scholes price, and we should be charging this price. And you ask the quant that question, and the quant says, no, that's not what's happening. This is the same price. And you'd be like, well, that's interesting, let's try some examples. Apple is 100, vol is 20, the forward is 100, 6 months, what's the price? You look at the two models, they're close enough, they're within a penny of each other. You do different problem, you do a bunch of problems, it's always the same. So now you might ask the question, well, why is it the same? And the answer is going to be that this distribution, this bushy tree, this tree that we created, with the 100 nodes, accurately represents the probabilities associated with the log normal distribution. Now, mind you, it's discrete because you only have 101 steps, where the log normal's got that whole bell curve, the whole skewed bell curve that a log normal is relative to a normal. So there's more content in, but you might find that with only 100 nodes, you can accurately price a vanilla option to like a tenth of a penny. And you might say that's good enough. Well, that's a good thing about it. Now, this would take longer than a closed form solution, so you would probably reject it on that grounds. But what you can do with this tree that you cannot do with a Black-Scholes calculator. We don't have a formula for American style options. What makes the American style options American, quote unquote American style? It's just a name, but I don't know how they came up with American and European, and then later Asian to represent averaging, right? But in the end, what the key feature of the American option is that you can exercise it
Early.
any point prior to maturity. It has early exercise feature. That is a unsolved mathematical problem. I mean, people are perfectly happy with the approximations they have to be accurate. So the American option problem is use the exact same geometric Brownian motion, and Black-Scholes up to the ND1 part come up with an exact answer of what that price is. The American option, you say, well, it's the exact same option, it's the exact same geometric Brownian motion, but at any point along the way, somebody could say, I'm going to exercise right now. And the exact answer to what that's worth is not known analytically, but people have plenty of good approximations. The first commonly used approximation was the binomial tree. And what you do with the binomial tree, you say, let's say I get to that node S0 u to the third, right? And the question you have to ask yourself is, should I exercise or should I not? And the way that this problem gets solved is you take all the final nodes, and on every final node, you compute the payoff. If it's in the money, you get some money. Deep in the money, you get more money. If it's out of the money, you get zero. So the bottom of the tree for a call option would just be a bunch of zeros. They didn't finish in the money, you got zero. But sitting at the top node, S0 u to the third power, you're looking at the future now. And you're saying, if I go up, I might make $105. If I go down, I might make $102. But if I'm sitting at U3, I could now make $103, some number in the middle. So the question is, should I just cash out my chips now and collect the money? Or should I roll the dice for one more time period in order to take, I'm running a risk. If it goes up, I make more money. If it goes down, I lose money. What's the best option? And that's the way the American options are priced on a binomial tree, just by starting at the back. So all of the payoffs are computed at the back. And then there's a bunch of math we can do to roll this thing backwards one step at a time. And every step of the way we say, should I exercise or should I not? Until finally we get back to the tree. And what happens is we take this tree for spot prices, we duplicate the tree with another tree right underneath it, and that's the value of the call. And we populate that call option pricing with the discounted payoffs, and we come up with the price. Okay? Now before I leave this topic and go to Monte Carlo, let's see if I have another picture here. This is a good example here. We'll look at that in a minute. I want to do a quick so ultimately, what is computing a Black-Scholes price about, right? The Black-Scholes price is given by, given ds equals, r minus q s dt plus sigma s dz, right? The Black-Scholes formula is that the call option price at time t plus the drift times the spot price times dc ds, okay, plus 1/2 sigma squared, the spot price squared, d squared c ds squared minus RC is equal to 0. And then not S, but C, the value of the call option at time t is equal to the max S at time t minus K, 0, right? This is the Black-Scholes partial differential equation. with terminal condition. Okay, so this is the equation, and this is the condition, right? And there's a stochastic calculus that tells you how you proceed from the geometric Brownian motion to the partial differential equation satisfied by derivatives under that partial differential equation. It's called Ito's lemma, after a Japanese mathematician from the 40s, 50s, I guess. Okay? And the ways we've talked about, well, what Black and Scholes did was they started with the partial differential equation, they solved the partial differential equation, and out pops the Black-Scholes formula. What was their big innovation? Their big innovation from, say, Samuelson, right, was that they replaced mu, the unknown drift of the asset price, by R minus Q, the so-called risk-neutral drift. They only had R, they didn't have Q, right? And that they presented an argument in their 1973 paper that said, because you can buy the stock to hedge your exposure to the call, this product has no risk. And since it has no risk, how much should it be worth? Well, it should be worth the payoff that you're going to get on average from it, discounted back at the risk-free rate. Previously, with mu, you could say, hey, you know, if mu's really high, obviously call options are going to be valuable because mu says this thing is going up. But the problem is, not only do you not know sigma, you also don't know mu. How much is the stock expected to go up this year? Who knows, right? People can guess, but Black-Scholes says, no, don't worry about that. You're going to use delta hedging to hedge your exposure to that gain, and you just have to worry about specifying sigma. So they solved that partial differential equation. Others there was a whole other way of getting to this. It's kind of interesting that a partial differential equation leads to a solution that has probability in it, right? There's kind of a deep underlying connection between the mathematics of probability and the mathematics of partial differential equations. And Ito's lemma is one of the things that tie that together. So another way, besides the binomial tree is essentially a way of simulating or giving a discrete representation of the geometric Brownian motion and saying, okay, I know all of these prices on the tree. I can use that to come up with an estimate for the value of the option by that sigma formula I put up there a few minutes ago, right? This guy right here, yeah? Moreover, another way to solve this problem would be to solve this partial differential equation either by a closed form, which is what Black-Scholes did, which is nice if you have a closed form. This one turns out that this is a kind of a hidden in there is the normal distribution. That's kind of the interesting part, right? It's essentially what's called a diffusion equation. We talked about, you know, if I had like, let's say this was a tube of liquid, right, and you know, kind of long cylinder, and I went right over top of it. I dropped a drop of blue ink or food dye or something, and watch the food dye disseminate throughout the liquid, the medium. The process by which it disseminates is called the diffusion process. Similarly, if someone blows a single particle of smoke into the air, and we just watch the smoke kind of expand into all the particles kind of start going over. That's another example of the diffusion process. And turns out that diffusion process, in one good rendition of it, is that, you know, so let's go back to I dropped a drop of ink or food dye in the water. What will be the density of blue particles throughout the tube, 1 minute from now? Well, it turns out the average particle will still be right in the center where you dropped it, and the particles will have spread out along the tube. But are they more likely to be close to where they started, or really far away from where they started? The answer is they're going to likely, on average, going to be close to where they started. And in fact, they're going to basically fill out a bell curve. Some of the really fast particles somehow will have, just through randomness, have escaped the outside. Others would have been randomly up, down, up, down, up, down, never moved off the middle. This is the connection right, that Brownian motion was defined, was observed by Robert Brown, and ultimately Einstein gave the explanation, which was caused by random interactions by subatomic particles. Norbert Wiener put it together and came up with a solid mathematical foundation so that you could do a lot of work with it without worried about making mistakes. So to solve a partial differential equation on a grid, if you don't have a closed form solution like the normal distribution, what you do is you draw a grid, and this is a grid in the way this particular grid is laid out is you say, maybe spot price will get down to 0. Or maybe it'll go to some crazy number like Apple goes to 1,000 in the next year from 100. Always using 100 as our base, right? So you say, okay, these are all the possible prices. Now, of course, 0 really is the bottom price, but the max is really infinity, because in theory it could go to infinity, but you're going to say it's so unlikely to exceed S max, I'm not going to worry about it. And then what you do over here is you build out a time step ladder. So T in our case is 1 year. Delta T might be 1 day, or it might be 1 week, okay? And what you do is you start by populating at node T with the final exercise price. What's the final exercise price? Right, we had that in our picture here, right, which is that at every node, you've ended up here, okay? And the numerical solution of this equation just says, I'm going to populate the final nodes with the value of the option upon exercise, and I'm going to, on the lower boundary, we actually have to define a condition at every boundary. The lower boundary, the option is worth 0, okay, because it can't escape 0. On the upper boundary, it's just going to be S max minus K. And then there's a set of relationships, much like the binomial tree, that enable you to start from the final time t and roll it all the way back to populate the value of the option at every one of these black dots. And the one you're interested in is going to be the one in the middle, because that's where S is right now. Okay, and that'll tell you the value of the option. And all you're doing there is you're building a thicker version of the binomial tree. The binomial tree is only the triangle that starts in the middle and goes to the edges, where the partial differential equation solution is going to consider more possible values. Turns out there are very efficient ways to solve partial differential equation values. And again, you could solve the American option problem using the same imposition of the early exercise condition at every possible step. Okay, finally, the last numerical method we'll almost spend time on in the next, after the break, we'll talk about it now, is what's called Monte Carlo simulation. So a kind of a interesting problem is how could you calculate pi by randomly sampling points in the square? So for this exercise, we want to think of this as being the unit square, which means it goes from 0 to 1 on the x-axis and 0 to 1 on the y-axis, okay? And what you could do is generate 1,000, let's say 1,000 random numbers to function as x coordinates, and then 1,000 random numbers to function as y coordinates. And you'd want to do this uniformly. So every number between 0 and 1 is equally likely to be selected for the x's. Every number equally likely to be selected for the y's. And in this case, we'd assume that the x's and y's are independent of each other. So 2 normal variables, right? What you would do with each point, so let's sketch this out a little bit. It's kind of so we take a unit square, I'll put the axis here. We'll draw a circle. I had been smart, I would have drew the circle first, of course. Okay. There's a unit circle. So what's the area of the unit circle?
Pi r squared.
Area is equal to pi r squared, right? And so since this is a unit circle, the area is pi, right? Well, this is really a, I think it was, I'll acknowledge my mistakes. This is a 2 square, okay? Because the circle is, it's 1 unit across to the center, another unit here. Okay, I could have just made a different circle. That's good enough, right? So what's the ratio? Area of the circle divided by the area of the square.
Pi over 4.
Pi over 4, right? Thank you. This is about 0.78 or so. Okay. So if you shoot 1,000 random numbers at this, so this is approximately, it's about 78%. You can calculate it on your computer if you want. Okay. If you shoot 1,000 random numbers into that random dots into that square, right? What's the probability that it should be inside the circle? If I pick, I just take a dart. Let's say my dart, I'm very good at darts. Every one I throw is going to be equally distributed between 0 and 2 on the x-axis and between 0 and 2 on the y-axis. What's the probability my dart lands in the circle?
78%.
It's pi over 4, right? Because of all the, I can hit any one of the points inside the square equally likely, right? But only pi out of the 4 units are going to be in the circle, right? So the area of the circle is 3. The area of the square is 4. Probability I'll get a point in the circle is 3/4. What's the probability I get a point right on the circle?
0.
Good answer. Why is that?
Because it's a line. It didn't have any.
Right. Probabilities cannot be defined for lines. They have to be defined in terms of area. Lines don't have area. The main problem is that you can't define it sensibly. It's like saying, what's the probability that the normal distribution is exactly 0? There's no sensible way to do that because there's just so many numbers between minus infinity and infinity. You can't give each of them a weight in a way that makes sense. You can only say, what's the probability it's between 0.1 and negative 0.1? That's a probability. It's got to be an area. Very good answer, right? Okay. So one way to use randomness to estimate pi is you'd shoot bullets at this thing, or you shoot random numbers at it, and if we got the sample proportion. Let's just say, we shot, 1,000 shots in, right? And, 791 went in, right? So we would have that 791 is approximately pi over 4. And that would tell us that pi is approximately 4 times 7, let's make it 800, let's say. Okay, it's easy enough. Okay, over 1,000, right? So that would be, I would say that pi is approximately 3.2. Not a great approximation of pi, but pretty good, right? And if you want to get a better approximation of pi, you'd shoot 10,000 random numbers at it, and then you'd get much more accuracy. So that's what Monte Carlo is, first of all. The main use of Monte Carlo is you want to estimate a probability of something, okay? And what you do is you generate random numbers, and you say, as long as those random numbers are generated according to the true distribution of the thing we're trying to estimate, then this is a pretty good approximation of pi, 3.2. And I only did 1,000 random numbers, which your computer would do, before you finish blinking your eye. Yes.
What I've learned from Monte Carlo is that there's heavy computational costs and that it's pretty time sensitive.
It could be time sensitive, time consuming.
So
right?
my question
Yeah.
is in regards to pricing derivatives
Yeah.
on a desk, in a real world application. How does that go about with respect to Monte Carlo?
Right. So it is true that, like, in the second half of the class, we'll price our Black-Scholes option using Monte Carlo, right? It's true that the Monte Carlo method might take 1,000 times longer than the closed form solution, but in the case of the Black-Scholes, it won't really matter. First of all, if we have the closed form solution, we're going to use it. That's very true, right? But where the Monte Carlo comes in is if we don't have a closed form solution. Our payout structure on the call option is very simple. In the money, you collect X. Out of the money, you don't collect anything, right? But other problems can be much more sensitive, much more difficult to model, and that's where Monte Carlo comes in. Okay? And the answer is, if there's enough money in a deal, you would just buy a bigger computer and let it run longer. And computers are much faster than they were when I came out and started working around 2000. But even then, it was like, okay, before parallel computing became run on GPUs and stuff like that. Let's say we would have a server farm, 192 computers, and the night run would take every trade and farm it out to the server farm and then combine the results back. You can do the same thing with a Monte Carlo simulation. It's going to take something that takes a long time to run. You farm it out to a couple of computers and then combine the results. Now let's take a break because we've been going at it for a while. We'll take a break till about 8:05, okay?
快2个月下周，有可能，他可能一会儿会说的。你照啥？
我不想听。
加油！上周刚考完。
对啊，上周刚考完，但是他其他的课不都是，就是最迟31号能结束，他这个可能要拖到8月份，应该不至于。他得给我们放暑假。
也就是下周考。
这怎么还不说？一般都上课前说的吗？
这课就说了。
I mean, email.
understand.
Oh, he was unmuted and there was like some sounds like playing in the background and
While you guys were presenting?
yes,
Oh
in
my
the middle of
God.
presentation and we couldn't mute him and Professor came and he couldn't mute him and I think he finally, I don't know if he just lowered down the volume of the
Yeah.
computer but the call.
Yeah, I called him and I said, are you still in the meeting? He said, I just left. And I said, you know, you're playing music.
Yeah.
out
Oh, you
loud."
logged in?
No, I was on
Yeah.
the train. I had text me to tell Loki to.
Yeah, it took a while for finally like decide that it's lower down the
That's
volume.
funny.
So I stuck and I was like, let me text you so I know you will call him.
Yeah, because he was apparently he was walking his dog or something while in class. Yeah.
That was so funny.
Yeah, I would probably agree. Especially nowadays.
You guys got package to leave early
Yeah.
yesterday.
What time did you end up leaving?
9:40.
That's crazy.
Yeah. Like, oh my god, I'm just gonna go home now.
When I start watching the show about the US and Turkey,
Oh, Industry. Yeah, it's pretty. They're filming season 4.
Yeah.
There is a lot way better shows to watch. Mr. Robot.
Right, like finished it.
Well, finish those. I think. What is that?
Last 3 episodes.
Yeah, because I saw where you were at.
Yeah.
That starting at, I think there's 2 episodes left.
It was like 3.
This episode has everything crazy that occurs. Yeah, it's, I mean, it was a phenomenal show.
I mean, it seems like everything's like calmed down and all like shut down.
Yeah, just wait and see. Can't spoil it for him, there's only one episode 4 of season 1. So. But text me when it finished because.
Yeah. I mean, I have like.
Yeah, what a show. I mean, the fact that it was.
The thing I texted you about that shit.
Yeah. But the fact that like nobody really saw it when it came out in 2016.
Well, I think they won like an award for
Yeah,
it.
yeah.
Because I recognize the name Samus.
Yeah.
And then I know Rami Malek because
Well, he's huge.
he's huge. Like, I think it was a Bohemian Rhapsody.
Yeah.
He won that.
Who's that?
Rami Malek.
He won the Academy Award for that,
Okay.
an Oscar. He's in that new movie on Hulu, right? Or Paramount.
We're watching, well, I just finished Mr. Robot. He's,
This Robot was kind of cool.
yeah, fantastic show.
I don't know if I watched the last season, but I watched a lot of it. It was good.
Yeah. But in fact, it was on like USA Network,
Yeah.
and nobody
Nobody
it
watched
seemed
it.
like nobody, and then Netflix just bought it.
Oh, they're gonna do, okay, good.
So now Netflix is streaming it, and it's going pretty viral. And when I got to see it, I binged it very fast.
He's got a movie called The Amateur from last year, I think, or this year even. Just appeared on either Hulu or Paramount. It was pretty good.
Yeah.
Yeah, he plays a
character.
CIA analyst.
Oh yeah, of course. Like an edgy-esque like.
Yeah.
It's with, Mullet, is it?
No way. Yeah, he's nothing. Who he play?
Yeah, he played Freddie Mercury. Yeah. You're gonna end up seeing it.
There's so normally talk to them these episodes after for this. What do you think? You know, I talked about that. Previous episode.
Check. Okay, you ready? So, the point here of this, this quick sprint through this section is not that I expect you to do these things, generate one of these trees, but just that I think it's good that you have an idea what's going on. Going back to the question about, Monte Carlo is time consuming, can you use it on a desk? One of the places where Monte Carlo comes, a couple of ways Monte Carlo comes into its own utility. One of which is if you have multiple different underlying assets in a transaction. Say you've got a transaction which depends on the level of, it could be Apple stock, it could be Apple stock and the price of oil, it could be Apple stock and the price of oil, and the short-term interest rate that the Federal Reserve sets at its meeting in summer of 2026, right? These are very different processes. You can do a lot of commodity modeling using geometric Brownian motion, but there are reasons why that's not necessarily ideal in some contexts. Interest rates, Fisher-Black of Black-Scholes did create a interest rate model which enabled you to price certain interest rate options using the Black-Scholes formula, but other more interesting interest rate options require specific interest rate models, which you will probably see, I think, next semester, that involve the evolution of interest rates. And these are very different stochastic processes. They all have a DZ term driving them, but they also have, they're not all geometric Brownian motion. We might see something like this. Examples of multi-factor stochastic processes. So multi-factor just means, when you see stochastic, remember it's just the Greek word for random. It just means it's a process with a probability distribution driving what happens. So stochastic process is a process where, generally speaking, in each moment in time, whether it's continuous time, every minute of the day, or discrete time once a week, once a month, whatever discretization you use, right? They all involve a family of random variables, right? Like what's the price of Apple in a week? That's a random variable. It's between 110 and it's between 105 and 95. What's the price of Apple in a month? It's between 110 and 90. What's the price of Apple in a year? It's between 150 and 50. These are, but these processes are linked. The geometric Brownian motion says I can tell you what's happening to the distribution of possible Apple futures at every point in the future under the assumptions of my model, right? Multi-factor just means there's two different kinds of multi-factor. One would be where you have many assets and every asset gets its own process. So let's talk about that one, One. Oh, my thing dropped. I just bought this Apple Pen because I couldn't find mine. When I was leaving the house, the magnet on this thing isn't that good. It keeps disappearing on me. So case one, multi-asset options. So example of this would be, let's say, a basket option. Payoff equals the max let's say it's 1,000 times, let's just keep it simpler. 10 times Apple plus 20 times Google, minus, I'll just say plus for now, plus, 30 Tesla, minus, let's just say that's, let's just pretend it's worth $1,500 and 0. Okay, so this is a call option, right? But instead of being a call on a single asset, you have some basket of assets, Apple, Google, and Tesla in this case, and there's some number of shares, okay? So if you exercise this option, you got to put $1,500 up and you get back the basket, 10 Apple, 20 Google, 30 Tesla, okay? Maybe 1,500 is the wrong number, maybe it should be 17,000. I don't know what those prices are off the top of my head, okay? So now you have multiple assets, and you could just say, look, I've got DA for Apple, equals, let's put DA over A, it's simpler, mu DT plus sigma Apple, DZ Apple, and Google is equal to, this is mu Apple, this is mu Google DT plus sigma Google DZ Google, and that should be DG over, okay, and then D Tesla over Tesla is some mu Tesla plus some sigma Tesla and DZ Tesla. Okay, so now the mu's all have R minus Q essentially, where the Q is the continuous analog of discrete dividends for each of those individual stocks. Could be 0 for the dividend. The volatilities are the various volatilities of the asset for the time period under question. And then there's 3 different Brownian motions. One that is the arrival of information that's related to Apple. One of which is the innovations, as they're called, of what impact Google moment to moment as we go through the day, and similarly Tesla. But these random sources of randomness, of course, are correlated. Some news comes out, impacts all 3 companies the same way. Some news comes out, good for Apple, bad for Google, and so on, or very good for Apple, okay for Google, neutral for Tesla, or some different newses, right? So and we capture that by saying that there's a correlation structure. There's a correlation structure which just says that the relationship between Apple and Google randomness is given by a correlation between Apple and Google times each time shock. There's one for Apple with Tesla. And then there's one for Google with Tesla. And these can be encapsulated into a covariance matrix. This one here is going to be the variance of Apple, the variance of Google, the variance of Tesla. And then over here you have the covariance, G, T. And you'll notice I use the same subscripts for both of these elements and every other symmetric element in the matrix. And that's because the correlation of Google with Tesla is the same as the correlation of Tesla with Google, okay? You compute those two numbers, they're always going to be the same number. It's positive. Doesn't matter how you organize the calculation, you get the same answer. So how many unknowns are there to determine in this? There were 3 assets. How many correlation pairs are there?
There's 6.
Close. So first of all, there are 9 elements to the matrix. So in some sense, there's 9 elements. However, 3 of them are not correlations. They're just
Okay, so
all
it's
variances, okay? And then the other 6 are actually in pairs. You need the matrix to look like this, but you only need the top 3 numbers to get the bottom 3 numbers. So the general rule would be n times n minus 1 over 2. So 3 times 2 divided by 2 is just 3. Okay? And you can see if we're going to have, if we're writing this out in math, instead of using A, G, and T, we would just use 1, 2, 3, 4, up to n, however many assets we have, because we could be bothered with a different letter for every object, right? Okay. And you may have, you studied CAPM market model, I think, did you not? In first semester, I believe, right? And in the CAPM model, what you learn about, CAPM relies on the, well, not the CAPM, but the Markowitz model, I should say, right? For the, what's the optimal portfolio, right? Learned about the market model, right? The market asset, I should say. What's the efficient frontier? Remember the efficient frontier? Important idea. Won a couple of Nobel Prizes back in the 50s, I guess, or the 60s maybe, for the work. Maybe they get awarded for the 90s. The efficient frontier is just, variance and mu and sigma are all that's important in a way, right? And it's inefficient if you're willing to take a bigger sigma to get the same mu, right? Why take more volatility to get the same expected return? It's also inefficient to take lower mu for the same sigma. Why accept the same return if you're taking on more volatility? Efficient frontier is that hyperbola, and then one of the things you learn about is that diversification is the story, right? In order to reduce the variance of the assets in your portfolio, you want to diversify. And across the broad market, you end up essentially owning the S&P 500 is what it boils down to, right? But you learn in that process that the challenge that they faced, especially back in the 60s, let's say when they were first thinking about this, is you have the S&P 500, you've got 500 by 500 matrix. And using the math I just told you, it's going to be 500 times 499 divided by 2, because of the symmetry, right? And that's, just say it's 500 squared is 25,000 divided by 2. 12,000 correlations you have to estimate, right? So that was kind of a challenge there. But, you don't always have that many assets under consideration. But the CAPM model kind of changes the thinking a little bit and says, look, there's the market, right? And then there's your beta to the market. And all you got to worry about is your own assets correlation to the market and the ratio of the two volatilities, and that's your beta, right? But if you wanted to price this option, how would you price this option? Well, Black-Scholes gave you the answer for one asset, right? The call option for one asset. And Rubenstein and stuff and Reiner in the 80s and the 90s came up with all these funky formulas for knockouts and double knockouts. All of those formulas, by the way, are just fancy math that some professors at California decided, they were good at math. Right? They said, what about this? What about this? And they did exactly kind of what Black and Scholes did. They figured these things out in terms of probabilities. They came up with closed form solutions and left the market to deal with questions about skew. Right? But here you say, well, look, even if I can't come up with a Black-Scholes closed form solution for this, I can assume that these things evolve according to these paths. The shock in A is a drift plus a sigma. the shock in Google, and similarly the shock in Tesla. And the shocks are not independent. On average, if Apple's having a good day, so are the other two stocks. If Apple's having a bad day, probably the other two stocks are too. If the market's doing zero today, they're probably all making zero, because that's just the big assets especially move in tandem since they're exposed to the larger US economy, right? Tesla maybe has more leverage, so its sigma is higher. On good days it makes more, on bad days it loses more. But in general they're moving together. So you can run a Monte Carlo simulation where you simulate this process for these three assets, and you can price this option. Another way to do this is to assume that the sum of those three assets, essentially a weighted average, where the weights are, in this case, 10, 20, and 300, divided by, times the price divided by the total, the portfolio, you can assume that that's going to follow a single geometric Brownian motion. And you need a blended volatility, and we looked at that formula last week when we had two assets. We talked about, that's a three asset problem. So what you could do, before I move along further, right, is you could just simulate A, simulate G, simulate T, all in one shot, get to the end and say, is this thing worth any money? If it's worth money, you say, okay, it's worth $10, and that's one estimate of the value of this option. Then you run the Monte Carlo simulation, another path, and you say, is it worth money? And this time up, it's out of the money. Okay, you get a 0. So maybe you run 10,000 of these paths, and you average them up. How much did I make over each path? And divide by 10,000, and that's an estimate of the price of the option. Money to be received in the future. Always remember, if you're not getting it till the future, you got to multiply by the discount factor at the end. Okay, we'll see. There's some slides in Hull that talk about this. Okay. We talked about a related method, which was in the Margrave instance, right? Margrave was case number 2. Margrave said, look, you've got asset 1. I'm not going to mention the correlation matrix every time, but you should always assume there's a correlation matrix underneath the scene relating the Z's. You've got asset 2. And Margrave said the value of the payout, the call that depends on S1 and S2, I like to put S2 and S1 even though I'll put it the other way, and time to maturity is going to be equal to F, not F, but let's use his language, let's use the language from last week. It's equal to S2 times ND1 minus S1 times ND2, where D1 is the usual, it's the log of S2 over S1 times, let's call it e to the RT here, plus 1/2 sigma squared T, all over sigma root T. And then the question becomes, well, what's sigma? We got the sigma 1 and the sigma 2. We saw last week that the sigma here is equal to the first sigma squared plus the second sigma squared minus 2 rho times sigma 1 and sigma 2. Okay? We saw that. And this is not a approximation. This is a closed form exact solution. And by saying, it's exact to the extent that the world really consists of two assets following geometric Brownian motions, moving with the correlation rho that is accurately specified, i.e. you can see the future. But the point is that there's no shortcut in the math at the end. If all of the assumptions that you've made about d sigma 1 and ds1 and ds2 are accurate, then this is exactly the price. And it comes down to this blended volatility. And then we talked last week about the fact, if you own an option, a call option, is the world more valuable with big sigma or little sigma? We learned one thing in this class: long optionality. Do you want volatility? Yes or no? You want volatility. You own the gamma, you own the convexity, you want things to go crazy. You're hoping that your asset will skyrocket out into the tail. There's different ways of thinking about this. If you think about yourself as a gamma trader, spot goes up by $1, I sell my asset. Spot goes down by $1, I buy asset. I'm buying low, selling high. One way to think of it. Or another way to think of it is say, big sigma means there's a chance I'm going to get out into that tail and collect that big payout. That's another reason you want big sigma. So knowing that, this tells you that this thing is going to be, in general, happy to see sigma 1 go up and to see sigma 2 go up. But rho plays a key determinant. If rho is a big positive number, we talked about this, right? If rho is equal to 1, you know, rho equals 1 implies sigma equals sigma 1 minus sigma 2 squared, square root of that, okay? Rho is equal to -1, sigma 2 squared equals sigma 1 plus sigma 2 squared, and then rho is equal to 0. The sigma squared is equal to sigma 1 squared plus sigma 2 squared. So in these three cases, right, the biggest one is when rho is -1. You take the two volatilities and add them up, and then you square. The smallest one is when rho is +1. You subtract the volatilities, and then you square them. Obviously, subtracting is not going to be as good as adding, right? And then the middle case, 0, you add the volatilities. It's not maybe immediately By the way, look at the algebra. Just put a 1 in there and factor the right-hand side, right? You have sigma 1 squared plus sigma 2 squared minus 2 sigma 1 sigma 2, right? X squared plus y squared plus 2xy. Those things are easy to factor, right? Okay, from algebra 1. And then, you know, but the real case is rho is going to be some number almost certainly bigger than 0 and, you know, close to 1. It'd be 80% or 50% or 70% because of the fact that most financial assets move in the same direction. When the world's going good, everything becomes more valuable. When the world's, you know, having problems, everything becomes less valuable. They move up together, they move down together. Now, this is an exact solution, but we could do the same calculation that we did here for the 3 asset case, except no longer would the payoff be exact. It boils down to the fact that the sum of log normals is not itself log normal, but a common way to price basket options, which is what we call this Apple, Google, Tesla structure, is to assume that the sum is really a log normal, and then compute the sigma log normal, and then just stick it in the Black-Scholes model. It's not a bad choice, and but you know, as a model validation person, you want to ask yourself, well, you know, the reality is the Monte Carlo, although it's time-consuming and it's got an element of randomness to it, so it has errors around it. The Monte Carlo is going to give you an accurate price. You may have to if you run like 1,000,000 pads, you should be able to get a price that's pretty accurate. So you would take your closed form solution, relying on the sigma 1, sigma 2, sigma 3 calculations similar to Margrave, and then you would compare the two results and say, you know, is this good or is this not good enough? Okay, so that's an example. But now, another interesting case where Monte Carlo would come up is if you have, you know, let's call it a multi-market option. So the multi-market option, you might have an asset like a normal geometric Brownian motion. And then you might have another asset, say like the short interest rate. And a common model for interest rates is This is called the Vasicek model. You may cover this in the fall. I used to cover it when I taught that class. AKA the Hull White short rate model. For R of T equals the overnight LIBOR, SOFR. You familiar with SOFR and LIBOR? LIBOR, was famously, for a long time, the model, the global standard for interest rates, and a big scandal blew up where it seemed like they had good evidence that said bankers at different banks would talk to each other about whether it would be better for them for LIBOR to be high or to be low that day. Every day at 4 o'clock or 11 o'clock in the morning US time, 4 o'clock London, I guess, or maybe it's 11 o'clock London time, 20 banks or so would submit a number to the banking authority, or maybe I think it was the authority that collected it. And it would say, look, for 1 month money, I'll lend money at this rate. For 2 months, I'll lend money at this rate. For 3 months, for 1 year, and so on. These are the LIBOR rates that we want for every major currency. And those rates would become published in the Wall Street Journal and other places. And they get used by a lot of contracts all around the globe to set markets. So for example, if you have a floating rate interest on your mortgage, it might reference the fact that you're going to, for the next year, you're going to pay 1 year LIBOR plus 200 basis points, let's say. Or that's kind of the common example. You might have a commercial loan that does the same thing. And but every bank has a position. They're either on a given day, either they're going to be paying LIBOR net for a year, let's say, or they're going to be earning LIBOR net for a year. Obviously, if they're paying, they're hoping they can pay less. If they're earning, they're hoping they can earn more. Now, the point of the market survey is each bank is supposed to indicate what their fair rate is, which they would be willing to offer money today for the next year. But bankers were found to have potentially been colluding with each other, talking to each other on the phone or at the bar or in text, saying, it would be great for me tomorrow if the 1 year LIBOR rate came in on the low end. And low end might just mean, look, people, maybe the real rate should be like 410, and maybe people manipulate the market so that it comes in at 408 as opposed to 410. Or on the other side, maybe they manipulate it up to be 412. 2 basis points might not sound like a lot, but if it's on, $5 billion of notional, 2 basis points could be, $500,000, $100,000, or maybe $1 million. Do 0.002, so that's 10 to the minus 4. 5 billion, 10 to the 9. So yeah, that would be $10,000, I think. You can work that out, okay? But real sums of money were involved. Ultimately, it led to LIBOR being replaced by SOFR. That's the first step. Why did SOFR come into place? Because it was deemed that the people who were creating LIBOR were unreliable, and people went to jail. 2 British bankers in particular served terms, one of whom served 4 years, and he got out in like 2019. Another one was sentenced to 15 years. They shortened it to 11. I think they let him out like after 7 or 8 maybe. And just today, the British High Court ruled that the jury instructions in his trial were unfair to him, and they overturned his conviction. So that's the way life is. But so the short rate is typically like overnight lending rate, or could be Fed funds, right? And this model says the change in the short rate, so DR, is equal to alpha R infinity minus R0 times dt plus sigma R dz. What do you notice about the difference? There's 2 main differences between the first equation and the second equation. And maybe not surprisingly, one of the differences is in the drift, the dt term. The other difference is in the diffusion, the DZ term. By the way, these should be different DZs, so I should have put a DZ here. I should have put a sigma S here, okay, just for, okay. Now this R, in this case, would actually be the same R, perhaps. Instantaneous rate of money would be the, you know, the thing you're modeling, okay. New pencils, happy, it's got 100% now. So what's the difference in, let's take the most important difference, well, let's take the volatility difference. What's the difference between the DZ term in the first model, the geometric line of motion, and the DZ term here? And I'll give you a hint. You need to look at the left-hand side of the equation to see where the difference is really happening. Or, put it another way, if I put the S here, okay, so putting the two models on equal footing. The change in S is the drift times S, dt, plus the volatility times S, dz. So what's the difference between the diffusion terms, the Z term? In the top one, ds is a volatility times S, right? dz, geometric Brownian motion. What about in the bottom? Does R appear in the diffusion term? Notice that the sigma R, right, is not proportional to R, right? This, you know, make this a little bit clearer. Okay. So you can see in the second equation, in the first equation, which we often shorthand by putting the S on the other side, just because it's quicker to write. I don't have to write S only once. But in the first equation, S gets multiplied by the volatility, and then the dz comes in. In the second equation, R is not involved. So the first difference is this is log normal. Log normal. This one is only normal. So this says that the changes in interest rates are normal. What this essentially means is that Apple goes from 100 to 1,000. We expect tomorrow's price change to be 10 times as big, just because the price is 10 times as big. But we don't assume that for interest rates. Say if interest rates are 5%, we think they're going to move 3 or 4 basis points a day. If they're 10%, we're still thinking 3 or 4 basis points. It's a model. Okay, but the decision is that interest rates really don't have that geometric property. What about the drift? What's different about the drift? Well, what does this drift mean? I'm going to take this over here. Right, the drift term. There's this R infinity, which in classical times we might assume is like the natural rate of interest rates. So up until the global financial crisis impacted, let's just say the U.S. for example, U.S. interest rates tended to oscillate around 5%. Sometimes it go a little high. In the 80s they went very high as a way to kill inflation of the 70s. Sometimes they go a little bit low because the economy is slowing down, so the Fed's cutting rates. But they would tend to navigate naturally back to 5%. It's only in the past 15 years where rates went as low as 0 and then got up to about 2%, but never really moved much about that until the great inflation of 2021, at which point they were raised to 5%. And now, so by historical basis, it's not uncommon for mortgages to be priced at 6 or 7 or 8%, but by the standards of 2010 and 2015, people look at 7% mortgages and they're really disturbed by it because it's high. Okay, but this says the R infinity is. Let me see if I got this right. Yeah. So alpha is called. This is called the mean reverting term. This is called mean reversion parameter. Okay? So an example, and it might be on the order of 0.10 for, just to give you kind of a concept. Let's say the R infinity is 5%, and let's say the current interest rates are 3%, right? So what this is saying is that the infinity rate, the place I think I'm heading, is 5%, but I'm only at 3%. So I subtract those two numbers, I get 2%, and I multiply by 0.1, I get 0.2%. And what this says is that starting from a level of 3%, if you solve this ordinary differential equation, ignoring the z, as you go out to infinity, the rate is expected to drift upwards back to its natural level of interest rate. But of course, the z term is actually bigger than that. And what it's going to do is sometimes it's going to go up, sometimes it's going to go down, right? That's what the randomness does. But the mean reverting model says if rates are higher than where I think it's expected to be, the model will push it down a little bit. If the rates are lower than I expect it to be, they'll push it up a little bit. And this is a property that rates are observed to have. There's some natural level. Now, in reality, our infinity changes from time to time. Like I say, in the 90s, perhaps 5% was a natural number up until the great financial crisis, 2008. Between 2008 and 2020, 2% was probably a more natural rate. When it went down to 0, it was like, okay, it needs to be here for a while because the economy stinks, but it's going to eventually drift back up towards 2. The economy gets a little strong, the Fed will let it drift up past 2. Now the Fed and the president are debating over what the natural interest rate should be at this point. And we'll see where it ends up. But right now it's been staying pretty, the 10-year rate is like 4%, I think, or it's been hovering between 4 and 5% for quite a long time. But that's the 10-year rate. This is a model for the short rate, which really means Fed funds, which I think it might be 5% right now, okay? And Fed funds is the only rate that the Fed really controls. The Fed, we talked about this briefly, but the Fed sets at its open market committee meetings and says, our target rate, they used to say it's 5%, but since the financial crisis, they've always quoted a range from 5 to 5.25. And the reason they did this was because when they got to the bottom of the global financial crisis, they didn't want to go below 0. So they started saying between 0 and 25. Typically, the market will trade like right in the middle of that. And the way the Fed controls that is if the rate drifts too high, the Fed will lend a lot of money at that rate into the market for overnight lending, and that'll drive the rate down low. If the rate's too low, the Fed will pull money out of the market by buying a lot of short-term securities. The long bond, it tends to follow the short rate, but it has its own mind. And this is where different presidents, Nixon, Carter, Reagan, currently Trump, have learned that the Fed, you can do whatever you want with the economy, what you think, but the bond market is going to determine your survival as a president. Because if the bond market doesn't like what you're doing, they're going to hike rates high. And what happens if the long bond is long? Mortgages are high. It's going to be a dread. If mortgages are high, people want to build houses. People are into construction. It has a pretty big ripple effect on the economy, right? So, the central banks have a measure of control over what's going on, but they don't have everything. So anyway, we have these two different models. One of which is mean reversion for interest rates. One of which is geometric bounding motion for some spot asset. And you could have an asset which says, I'll pay out on a call option, and I will gross up your payment by the instantaneous rate of interest that you sacrifice overnight for the past 10 years. So every night I'll let your asset grow at the risk-free rate of interest, 5% for a year. The next year it was lower, it got only at 3% a year. Then it got really high at 7%. It's kind of like an inflation protected thing, for example. And there could be an option that does that. There would be a cost associated with it, right? But you could do it, right? But you would need to model ds over s, and you need to model dr separately. You can't really do that and get a closed form solution. Maybe there are some weird cases where you could get closed form, but instead you'd use Monte Carlo. And we're only doing two assets here. Interest rate models actually tend to have not just one factor for the short rate, but they often have 2 or 3 or as many as 5, let's say, stochastic processes to get the whole shape of the yield curve. And that's another place where Monte Carlo will come in. Okay, now, let's just take a look at what Hull had to say about this. He has a few remarks. Oh yeah, so I wanted to take you back, let's finish the Monte Carlo talk and we'll go to that. Actually, we'll come back to the Monte Carlo, we've got enough time to do both. So, okay, this is the American style option. Is this American? No, this is a European. This is a European put option. So the strike is a spot is 50. Hull is humble in his days. I always go for 100. He says 50. The spot is 50. The strike is 50. Interest rates are 10%. Sigma is 40%. Is a high flying stock. T is 5 months. T will always end up being annualized at the end of the day. 5 over 12 is 4167. Delta T is 1 month. That's just, I'm going to take 5 steps and say. Okay. Not very accurate to only take 5 steps. You need a lot more granularity to really get the process. He calculates these parameters, the U, P, U, D, and the P, okay. He just works it out for you. But then he says, look, so this is what the tree looks like. So I told you there would be 2 trees. He puts both trees together. He says, starting from 50, if you get only up shocks, you end up at $89.07. If you only get down shocks, you end up at $28.07. Notice there were 5 time steps. You end up with 1, 2, 3, 4, 5, 6 places you can end up at the end of the tree. And then at every node, you just say, look, the exercise price is 50. So it's a put now. So if the spot's at 89, do you exercise? No. You don't give it to somebody, say, give me 50 bucks, but it's worth 89 bucks. Puts out of the money. All the up prices are out of the money. 70 is out of the money, 56 is out of the money. But if the spot price ends up at $44.55, the 4th node from the top, 50 minus 44.55 is $5.45. You would exercise the put option. Similarly, the other 2 nodes. Now, that's called the terminal condition in the context of the finite difference method for the partial differential equation. We've now populated the time to capital T, right? But now you want to go backwards. So how do you go from 2193 and 1494 to 1850? You might make a guess. What might your first guess be?
Interpolation.
Slightly different. Okay, let's say it's going to be a form of interpolation for sure. What's the interpolation going to look like? What would the simplest interpolation be?
You're gonna weight it by the P.
That's not the simplest one, but yes, that would be the right one, right? You could say, look, it's half it's going to go here, half it's going to go there. I'll just take the average. I'll call it 1850. But that would be not as good, would be wrong, so to speak, as, well, if the P up is 52% and the P down is therefore 48%, I want to apply those weights. 52% of 14 and 48% of 21.63. That weighted average is what sitting on this node, looking out at my future, which only has 2 cases, I see a weighted average price of 1850. Not exactly. Why is that? Because this is money I'm going to receive when I get there in 1 time step. So if the weighted average is some number, what do I have to do with that weighted average? I I gotta go backwards one period in time,
You
which
can
means I
discount.
have to discount, right? So this will be the weighted average, P times this, 1 minus P times this, add them up, multiplied by e to the minus RT, where T is 1 month in this case, and that gives you that node. You do that all the way on the tree, and you end up back here, and the final node is $4.49. In the case of the partial differential equation solver, instead of having this triangle, you'd have a full rectangle filled with nodes at every node, and the diffusion process is calculated slightly differently, but you essentially end up at the same level for 49. The benefit of the partial differential equation version is that it's numerically more stable. Okay? Now, and if it were an American option, right, you'd say, look, this thing is worth $18.50 in the future. Well, discounted back to today. So I said, if I continue, what I own is worth $18.50. Should I early exercise? We'd put we'd put a max of $18.50. How much is this thing worth in on exercise basis? It's $50 minus $31.50, which is actually also $18.50. That's a coincidence. The coincidence is this thing is so deep in the money that it's not surprising that this number is the weighted average. But there'll be some nodes on the tree, like maybe the $14.64, where the intrinsic value, let's see, what's 50? Unfortunately, all these numbers look like they add up to, oh no, look at this node right here. This pen doesn't do this on PDF, but if you, there's 44 in the middle, 44, 55, and 638, so it's one up from the red, $10.31. If you add them up, they are, what happens if you take 50 minus 44.55? What do you get? You get 545, right? So this thing at 638 is more than the intrinsic value. The intrinsic value is only, immediate exercise would only get you $5.45, whereas waiting gets you 638. That's the optionality, the chance that you might shoot down to this red node over here. But there might be interior nodes where instead of getting only $5, instead of getting this $6.38, it's conceivable that this interior node, immediate exercise might be worth $8. And if you were pricing an American option, you would cross out the 638 and replace it by the 8, and then keep rolling that back forwards. Okay. Of course, if early exercise was optimal here, it would automatically also be optimal here. That's kind of a homogeneity property of option exercise. Okay. Now to do the same thing with Monte Carlo, it works slightly differently. Oh, one last. For the Monte Carlo simulation, we do the following steps. We talked about these. We simulate a path for the stock price. Step 2, calculate the payoff. Step 3, do it many times, maybe 1,000, maybe 10,000. A question for risk manager would be, how many paths did you run for this? Step 3A would be, how big is your error? Right, so if you have 1,000 and you get a certain price, and if you do 10,000, well, actually, let's if you go from 1,000 to 4,000, what happens to your price? And the reason why I quadrupled is one of the basic properties of Monte Carlo simulation is that quadrupling the number of paths halves the size of the error. When you get a Monte Carlo answer, your answer should be some number like it's $5 plus or minus 20 cents, which means your Monte Carlo simulation, 2 standard deviations, 2 sigma, is between 480 and 520. If you want to cut that 20 cents variance into 20 cent standard deviation in half, right, you have to quadruple the number of paths. And then it would go from 490 to 510 if 5 was the correct central number, okay? All right, let's pause for tonight. Read the energy section that I sent out, chapter 35 in the book. That'll be our last, that big topic. I will be here next week, and you can come or not come. I will hand out some assignment for you to do over the next 2 weeks. I'll put up a slot for the programming assignment 2 to be handed in, as well as some instructions. If you are able to do assignment 2 without having more explicit instruction than what's in the code, like somebody here who is now gone. Did anybody do homework assignment 2, programming assignment 2 yet? Okay.
I could do it,
I gave you another set of Python files to compute a
Oh, I had trouble
volatility.
with that one.
You had trouble with
A
that?
bit more trouble than the first.
Okay, but was the instructions that are baked into the files enough?
Yes.
You don't really need a separate PDF saying do
Yes.
this, do that.
No, it was.
Okay, no, it's got more challenges, sir, it's got more calculations.
I could do it in Jupyter.
You do it in Jupyter's fine, Jupyter's okay.
The last problem, I get a different answer than yours though.
As you did the first time.
Yeah.
Okay, it's possible I have mistakes, this is a possibility.
I think it was just a minus to plus. The number was the same, it was just a minus plus.
Oh, yeah, it can't be both, so one of us has a mistake, and since you've been thinking about it, the odds are it's me. Which Greek is that?
It was the last problem, I don't remember. What it was. I actually did it weeks ago.